Okay. Yeah. So last time we discussed Frobenius reciprocity, and the proof more or less it's an adjointness kind of statement, and modulo this linearity of this pairing and the statement about orthogonality of characters of Schu's lemma. This is basically this adjointment statement. H equivalent map from W to V prime is isomorphic to G equivalent map from in W to V prime, where V prime is some G representation. So if V prime is a G representation, it is automatically an H representation. Yeah. So technically, this statement should be written. So this, I mean, if one wants to be completely pedantic, or one should write this as W comma res V prime. This H V prime. Yeah, so restriction of so I mean, as a vector space, it's the same vector space, and you just think of it as action of H, the subgroup H. Yeah. So this is let's say the definition of this is precisely this way. Yeah. So that is what Frobenius reciprocity is. There is another. So this you can think of it as some formula between ind and res of induction and restriction of class function. There is another formula which we did, which sort of I didn't explicitly talk about, but we have seen this for characters, let's say, or for representations. So ind phi dot c is same as ind of phi dot res c. Yeah. So so of course again you can so dot is multiplication. Yeah. So these are class functions, so you can multiply, like characters we multiply. Okay. So so if you start with a class function on H, you induce it to G, and then you get a class function on G, and if you multiply with a class function on G, you get a class function on G. And the right hand side here, if you have a class function on G, you restrict it to H, and then you get a, let's just put G and H here, so that's clear. Then you get a class function on H, you multiply it, you get a class function on H, and then you induce it to G. So your right hand side is also a class function on G, and this equality holds. So how does this follow? So if P and C are actually characters corresponding to some representation, then this we have seen. Yeah, it follows from follows for characters from what statement? So what is the left hand side if phi is a character of a representation? What representation?
The tensor.
The tensor, yeah. So so phi is a representation of W. Yeah. So if so it follows from this. So you have to in W. Yeah. So in W GH, you tensor it with some G representation, let's say V prime. This we saw is isomorphic to first you just take consider W as a H representation, and V prime, since it's a G representation, is also a H representation. Yeah. So so you can take the tensor product with V prime as so maybe one should write it so we are trying to do it very strictly. So this is tensor product of G representations on the left here. should make this distinction that V prime, now I'm thinking of it as an H representation. So this is a tensor product of H representation. So, and then you induce it to G. So this we saw when we started the discussion on induced representation. Yeah, one of the first few properties. So there I hadn't written this res G H B prime. I had just written V prime when we were discussing this, because I mean, in some sense, V prime is naturally a H representation. There is nothing. Restriction is sort of just for just looking at H, action of H instead of the action of the whole group G. Yeah, there is nothing funny going on there. So once you prove this for representation, then since we know this for representation, it follows for characters of this, and then of course you use the same fact that this linear, I mean, any class function is linear combination of characters, and of course multiplication is a bilinear map. Yeah, a multiplication of class function. Meaning distributive law, etc. holds. Yeah. So it, then once you prove it for characters, it works for all class functions. Okay. So you use linearity for arbitrary class function. So that's another formula involving int and res. So one consequence of Frobenius reciprocity, or this adjointness, is this. So let H be a subgroup of G and W be an irreducible H representation, and E be an irreducible G representation. Then the number of when you induce W to G, then the number of copies of E in this is same as the number of copies of W in restriction of E to H. Yeah, so E, when you think of it as an H representation, it may have some number of copies of W. Yeah, that number could be 0, but it could be anything. Yeah, so that number is same as the number of copies of E in W. So this is just a consequence of Frobenius reciprocity and the fact that irreducible characters we can, and the number we can figure out from this this pairing. Yeah. So what is the number of copies of E in GHW? How do we figure that out? So since so chi E is the character for E. Yeah, and so number of, maybe let's just write this. The number of copies of in GHW. So in GHW is some representation. We want to figure out the number of copies of E in this. Then what do? This is what we were doing. Yeah. So in GHW, you can write it as direct sum of irreducible representation with some multiplicity. Yeah. And since E is irreducible, if you pair it with the character of this representation, if you pair it with character of E, you will get that number. Yeah. So this is same as the pairing chi E with chi of this guy, GHW. Yeah. But this pairing, of course, is same as, I mean, we are in characters, so this pairing and that pairing agrees. So actually, this statement you can write it with respect to the other pairing as well. That doesn't matter. Yeah. Because for characters, the two pairings are same. For characters, you can write it for with either pairing. And in general, yeah, so otherwise it's conjugate linear. Yeah, so this formula is conjugate linear, so one has to be, okay. But for characters, these two are same, yeah, so it doesn't matter. So chi e, and chi of this is same as end of. So chi of the induced representation is the induced induced of the class function. Yeah, so in GH chi and chi e, and this this thing you calculate over G. Yeah.
So that should be chi W.
Chi W. Yeah, this is good. And this we calculate over G. Yeah. And this by Frobenius reciprocity is same as you restrict this chi e, comma so GH, comma chi W H. Yeah, and this is symmetric. So so this is same as chi W, or anyway, it doesn't matter how you do the pairing. So so this is same as chi W, chi of. So so of course restricting the character is same as taking the character of the restricted representation. Yeah, so this is same as chi res DHE. I mean, restricting the character representation, you're not doing anything essentially. Yeah? You're taking the same vector space, just looking at H action, which is number of copies of. So here this is since E is irreducible. If E is not irreducible, this pairing will be something else. Yeah, it will count something. I mean, then you'll have to see how many number of copies E has, and there is a meaning, but that's not it's not the number of copies of E, since E is irreducible. So this is the number of copies of W in this GH. So here, since W is irreducible. Okay, so that proves this thoroughly. Okay. Any questions or comments? Yeah. Okay. Okay, so today we'll talk about, we will get to, hopefully we'll get to Mackey's criteria, but certainly not the proof. We hopefully will get to the statement of Mackey's criteria. Yeah. So that's about irreducibility of induced, when induced representation is irreducible. So W is irreducible, then in the GHW has a chance of being irreducible. But not it. But it needs to satisfy another condition, which we will get to today. Yeah, it's about some conjugate. So I'll yeah. So there are two representations will cook up. One restriction of H to some other subgroup, and and then another representation which I'll cook up, and they shouldn't have any common irreducible representation. That's the other criteria. So I'll get to it, but so to define that other representation, we'll have to introduce this notion. Yeah, so we'll have to consider this situation. Yeah, so say G is a group, H and K are two subgroups of G, and let subgroups of G, and let W be an H module, H representation, H module. So you can, of course, induce it to G, and you get a G representation, and then restrict it to K, yeah, and you get a K representation. So we want to understand what this gadget is. Okay, so this understanding this will help us prove this Mackey's criteria. Okay, and we'll apply this when K is equal to H. Okay, so that will help us somehow. So you start with some representation, you induce it to G, and then restrict it back to H. But more generally, I mean, you can talk about more general when H is not necessary, K is not necessarily H, then also you can study and try to understand what this representation is. Okay, so we want to understand what this representation is. So we want to give a a different description. Yeah. So we'll use the usual notation. V will denote the induced representation from W of W to G, from induced from H to G. So we know what V is, yeah. So V is just the translates of X W, yeah. So X where X runs over all left cosets of H. Or you can run it over all representatives of left cosets of H. So each this XW depends only on which left coset you choose, not really on the representative. That we always saw. Okay. So among these left cosets, this will be related to double coset. This restriction of this G representation to K representation of this induced representation will be related to this double coset. Yeah? So it will be so this guy is a representation of K. Yeah, so it will be and of course the dimension of this is G colon H times dimension of W. Yeah, so this will be some K representation. So we will see that this direct sum of certain K representation. And those K representation are basically you club together certain left cosets. Yeah. So you consider this collection of double cosets. So have you seen double cosets in your group theory?
No.
No. Okay. So maybe I'll start with some discussion on double cosets then. Yeah. So it's not. I mean, it's not too different from left cosets. So I'll write down. I'll move this proposition a little lower. So it's basically combining all the left cosets with entries in K in one bracket. Yeah. So what is a double coset? So you consider. So what is KSH? So for S in G, KSH is like left cosets is elements of the form x, s, y, where x belongs to K and y belongs to H. Okay. So this is a double coset of K and H. So of course you can see that these double cosets contain all the contain some of the left cosets of H. Yeah. But like left and again like left cosets, these double cosets are either same or disjoint. Yeah. So KSH intersection K S prime H is empty or KSH equals KSH S prime H. So these are the only two prime possibilities for SS prime in G. Okay. So of course, if so I suppose this is clear, right? So for instance, suppose S prime belongs to KSH. Yeah. Then I'll show that KS prime H is equal to KSH, and that will prove the this above statement. Yeah. If S prime belongs to KSH, this implies S prime is equal to X SY for X in K and Y in H, which implies K S prime H is contained in KSH. Yeah, because any element here is some. So maybe I'll write it as X naught Y naught here for some X naught. So hence so a typical element here on the left hand side, because X S prime Y is then equal to X naught S Y naught Y for X in K and Y in H. And of course, this guy again is in K because K is a group, and this is in H because H is a group. So that tells you that this this is in. So this belongs here. Yeah. Okay. So further below. So. Bring it up if needed. So that is so you can see that double cosets are indeed either disjoint or identical. Yeah. So other inclusion also you can see. Yeah. Similarly, and or you can compare size. Yeah. So. If you are in the finite setup is equal to KSH, because if you take something here, you just you can show it also belongs to this guy, because you just take multiply by X naught inverse and Y naught on the left and Y naught inverse on the other side. Okay. Conjugate XY with X naught inverse, X naught and Y naught. Yeah, so this gives you so this gives you a partition of G like the left cosets. And in fact, what is KSH? If I want to write it as some in terms of left cosets, this is union of x sh where x belongs to K. Yeah, so it's a collection, it's a union of certain number of left cosets. Yeah. So those left cosets of the type x xs. Yeah. So if you're looking at this particular ksh left coset, so you have to look at. So of course there are many repetitions here because K is a group. Yeah? And only so xs and x prime s may give you the same left coset. In fact, you can figure out how many. So somehow, so of course, note xs h may equal x prime sh if x if xs so the sum inverse, yeah. So xs inverse x prime s inverse xs belongs to H, i.e. S inverse x prime x s belongs to H. Have I written it correctly? Yeah, looks like.
You wrote K in the end.
K, not K, but H. Yeah. So the two will be same if the two left cosets will be same if for two different elements. So x prime in K. Yeah.
x1 prime inverse.
X prime inverse. Yeah. That's right. So if x prime inverse x, when you conjugate by s, you get it lands in H. Yeah. So then the two cosets are going to be same. So yeah. So I'm trying to see if I can make some. So maybe I can one can rephrase it as x prime inverse x belongs to s s inverse. Yeah. So it should land in so there's yeah, so x prime inverse x should lie in this particular conjugate of H, conjugate of H by S. Yeah, so that is the condition. Okay, so this is how double cosets look like. Yeah. So now, yeah. So what do I want? Yeah. So now I want to sort of, yeah. Now I want to make this claim about what this restriction is. Yeah. So that. So you denote. So once you have a representation of W, representation of H, then we denote by HS this subgroup S inverse HS intersection K. Yeah. So it's a conjugate of H by S and you intersect with K. Yeah. And then you can define a representation of HS using the representation of W. Yeah. So you have we want to define the action of HS on W. So what is the action of HS on W? so given an element of HS, it cannot act on W directly because W is a H representation. So you conjugate it by S. Yeah. So you multiply this by SX S inverse. So this guy SX S inverse will land in H then. Yeah. And then you just act by, and then this action of W is defined. So that is this representation of HS. Yeah. So the underlying vector space is W, but the action is this. Yeah. So X dot W is SX S inverse dot W. And this makes sense because SX S inverse lands in H if X belongs to HS for X in HS. Yeah. So, so of course, if I use W as the underlying vector space, it will be confusing, yeah, because sometimes we don't write down the map to say the representation. So, so this representation will denote it by WS. So, underlying vector space is a copy of W, if you like, but the action is it has an HS action instead of an H action, yeah. And HS is sort of conjugate of H intersection with K. So another way to think of rho S is it's a conjugate action of H restricted to K. So I mean, for every X in this conjugate subgroup, you can define this action. So it becomes a conjugate action of S, and then you restrict it to K. That is what rho S is. Restricted to not K, but K intersection that conjugate subgroup. Yeah, so this and that smaller subgroup. So that is what this rho S is. Okay. So so now the proposition is that the representation we were trying to study, this induced representation of the induced representation of W to G restricted to K, that is isomorphic to you induce this HS. So this is this HS, you induce it to K. Yeah. So you induce it to K and then take the so you get induce this this representation which we just defined to K, and then you take so you get a K representation, and you take the direct sum of all these K representation over various double cosets or double coset representatives, if you will. Yeah. So this will depend only on, up to isomorphism. This will depend only on the double coset. Yeah. So sum over all double coset. So what I'll do is I'll use representatives. Yeah. So sum over all double cosets. So I'll just write it this way. Sum over S in S and KHS WS, where capital S is a collection of representatives of the double cosets. The collection of double cosets KSH SNG. So this collection of double coset is usually denoted by, and so left coset was denoted by G mod H. Double coset is in literature is denoted by the slash on the other side as well. Yeah. So this is how people write it. Okay, this in this collection, and of course you take any representative, any element in this double coset, that any two element in this double coset generate the same double coset. Yeah. So you choose one representative for each double coset, you make that set S, and you just take the direct sum of this. Then these two are going to be isomorphic. Okay. So that is the proposition. Okay. So let's see a proof of this. So okay, so V is yeah. So I hope I used yeah. So V is our induced representation. Yeah? So VB int GHW. Yeah. And so since V is in GHW, V is I don't know is direct sum of W or translates of W. Yeah. So XW X in G mod H, or maybe some representatives of left cosets if you like. So maybe I'll do that. Yeah. So I don't know if it will help. Yeah. So yeah. Yeah. So I don't know if it will help. So let's. So which representative we choose doesn't matter. Yeah. So yeah, but yeah. So X etc. X Y S. I want to use it for. Okay, so sometimes I'm using it for left courses, sometimes for elements. Doesn't matter, it's some dummy variable. Yeah. So V is, we know, is the direct sum of these left cosets. Okay, so now I want to define, so this is a G representation. Now I want to break V as direct sum of certain K representation. That is the goal, right? I want to write this this V, the restriction, when we restrict V as a K representation, I want to write it as direct sum of certain K representation. So there's a natural way to make it in, decompose it into some K representation, yeah, based on these elements of capital S. So for, there you go. So for S in capital S, let Vs be the subspace of V, which comes from translating. So Vs is the subspace which corresponds to those cosets which come from KSW. Yeah. So is the sum of XW such that X belongs to KSW. KSH. So this is not the right way to write. So I want to take only those left cosets. So X belongs to X in G mod H such that, and X is contained in K S W. Yeah. So there are certain left cosets. So as I said, these double cosets are contained in certain left cosets. Yeah. So these double cosets contain certain left cosets. So you take the direct sum of those. So you take those translates of W for which these left cosets are contained in this particular double coset KSW. Okay. So some of these left cosets will be contained in these double cosets, the others will not. So you just take that subspace. Yeah. So Vs is a subspace of V. Yeah. And of course, it is stable under K action. Yeah. So not if Y belongs to K, then YVS is is basically YXW X in G mod H, X contained in. So maybe you take a representative here. Yeah, X so I'm sort of conflating these two, but it's okay. Sometimes you choose. So X is some collection of representatives of G mod H, and X is in this double coset. Yeah, but this is same as so since y is in K, this is same as saying sum of yxw yx in G mod H and y. So these are also some cosets such that yx is contained in ksw. So xw and yxw make sense for any so xw makes sense for any left coset as well. So this notation is not bad, yeah. So yx is also a left coset, so yxw also makes sense, and so yx and x. So this sum is same as yx belonging to G mod. Yeah? So yx is an element of G mod H if x is an element of G mod H. And so this is just which is same as ws. Yeah. So vs is k stable subrepresentation of V, but now restricted to K. Yeah. So V less K. So V, you think of it as a K representation, then Vs is a K stable subspace, and hence a K subrepresentation. Okay, and also of course if you change S, then you will if you change take different S also. If S is not equal, if S prime is some other element of this this capital S, and S prime not equal to S, then Vs prime will be sum over some other left cosets, yeah, and these two will be disjoint set of left cosets. Otherwise, you know, the double coset will have some intersection. Yeah? So Vs prime is direct sum of Vs prime is intersection Vs is 0. Yeah. And so V is in fact direct sum of Vs as in S prime, little s in capital S. Okay. So they are linearly disjoint, and of course, if you run over all these Vs, then you would have exhausted all the left cosets. Yeah, every left coset has to be in one of the double cosets. Yeah. Basically, you yeah. So every left so KSH is some collection of double cosets, and of course every left coset is in some double coset, because if let's say x times S H is some left coset, then that will be in KXH. Yeah. So every left coset is in some double. So we get that you can write it as the x sum of these K representations. So V is, and since each of these Vs are K stable, so for every S, these are K stable. So and this is and this is as K representations or K modules, this decomposition. Yeah. So we have shown that this and this is the restriction of Vs. So you think of V as a restrict, you restrict V to K, and then as K representations they are. So to restrict means you put this notation, but essentially we are doing nothing. Yeah. Okay. So what remains to show is that, so we have shown that this decomposes as some collection of K representation. We want to show that these are these K representations. Yeah. So enough to show. So enough to show. Vs sorry. Vs is isomorphic to int KHS of this representation Ws, yeah, which was defined here. So Ws was this this representation. Yeah. So once we show this, then we are done, right?